In this video, we're going to use a PhET sim to explore what happens when particles collide. The simulation itself has several different representations. We're going to be looking at the tab involving a single collision. Here's the reaction that can take place when we have particle A smashing into the molecule BC. It could potentially switch places and we could end up with this new molecule AB and atom C left over. So that's the reaction. We can direct one particle towards the other one and we can impart kinetic energy on it. So we can shoot it there and consider whether we have a reaction take place by pulling the knob here. So let's try that. So I'll impart kinetic energy. Notice as I pull it back more, the temperature is rising. The temperature is a reflection of the kinetic energy. I see the particles bouncing around, but I did not see a reaction take place. So the kinetic energy added to the system, it increased the temperature. There were collisions, but I did not see a chemical reaction take place. Why do you think that chemical reaction did not occur? What do you suggest we could do differently to make a reaction take place? Let's explore it now, and we'll add some information. So here we have a representation that shows the energy, and you see as the temperature goes up, that total energy is rising. We have now the energy above where the products would be found. I'm seeing collisions. But once again, I'm not seeing a chemical reaction take place. So these two different representations where we have what's taking place with the particles and one that's describing the energy. Can you connect those two different representations? What questions do you have about those? We're going to be doing quite a bit with both of those within this video, and we need to be able to make sense of that. As I look at this, the total energy here, is that greater on the left-hand side or on the right-hand side of the reaction? And when I say the left-hand side, what do we even mean by left or side? Can you make sense of those terms? Once again, there was no reaction that took place following this collision. Why do you think we had no reaction? Now, in the sim, look at the details here. How can we increase the kinetic energy for atoms that are already in the container? Any thoughts on that? In this case, you see where the total energy lies. Let's raise the temperature by heating it up. We're adding heat. I see the thermometer is going up. The total energy is rising. Let's see if we can get a reaction. Nothing yet. Now I see a chemical reaction taking place. What do you predict will happen if we lower the temperature? Okay, we're back to having collisions, but no reaction. Crucially there, when we raised the temperature, we were able to raise the total energy that would accompany this collision. We had a chemical reaction take place when the energy of the collision was above this peak. That's called the activation energy. The reaction produced the AB plus C. It gave us the products, but we noticed it didn't stop. It would convert from one to the other, and it kept going back and forth with each collision. Why do you think it didn't stop? Take a second, share your thoughts on that. I would answer it this way. If there's enough energy to produce AB plus C and exceed that barrier for the activation energy, then there's enough energy to overcome that activation energy barrier going in the other direction. The collisions, if it's capable of producing the product, it was able to also then go in the other direction and lead to the reactants. That's how I would interpret that. So if I'm looking at this one, let's set up the sim this way. We're going to have it where the kinetic energy is going to be large, which is shown with a very high temperature, and the total energy for that collision is way above the activation energy. But I'm going to make a change here. I'm going to make it so it's not directed initially at the molecule, it's at this different angle. Make a prediction. What do you think is going to happen now? Let's explore that. We're going to take an angled shot. We're going to have plenty of kinetic energy. Okay, I see collisions taking place. Just grazed it right there. Let's see if we can have another collision take place. It's getting closer. Okay, another collision took place. But I've yet to see a chemical reaction. Notice even though the temperature is quite high, those collisions were not leading to a reaction. If they tumble around enough, I bet we have another collision take place. But we might need to wait. There we go. This equation right here, what's called the Arrhenius equation, summarizes different features that we were just exploring within that sim. We see that there is an energy of activation, this activation energy, which is going to be important. The temperature, which is the reflection of the kinetic energy, is also important. This leading term A is called the frequency factor. That has to do with aspects of the orientation for the collision. Oftentimes, the key things that we are going to be looking at are the activation energy and the temperature. The entire set here gets combined and describes what's called the rate constant, which is given the symbol a small k. How do these different parts fit together? Let's look at this example. Let's say this molecule here is considered the reactant. During the collisions, it leads to what's called the activated complex, and that could move on to produce the product. This would be a reaction progress diagram for that in terms of the potential energy. We have the initial molecules present. During the different collisions, they can become distorted as the molecule bends. At the top here, which corresponds to the activation energy, we have this higher potential energy, this more unstable molecule. From there, it can now move down and give us the new one, which we are calling the product. Now, this transition from going from the molecules described as the reactant to the activated complex, what do you think? Does that require energy, release energy, or there's no change in energy? As I look at it, it's higher in potential energy, so I think it requires energy within those collisions to move to that excited, activated complex. How about this one? If we say something has a fast rate, what do you think that means in terms of the rate constant and the activation energy? When something has a fast rate, it means it has a large rate constant. Small letter k is a large value. And that also corresponds to a small energy of activation. A smaller energy of activation, it's easier to get over this barrier, and that leads to a larger rate constant. Now, when we talk about these as far as reaction taking place, we've seen how it can go in both directions. It could go in a forward direction or a reverse direction. And we can think about the energy of activation in both directions. We can think about what does it mean to get over the barrier as I go left to right or as I go right to left. So within this example right here, take a second, share your work. What do you think is larger, the energy of activation when we're going forward or when we're going reverse? And what would that mean in terms of the rate constant? It looks like the energy of activation is smaller when I'm going in this forward direction. If I look at the barrier I need to get over, well, it's a lot larger when I'm going right to left than if I'm going left to right. And we've just seen that that would mean, in some ways, the opposite when it comes to the rate constant. Because it has a smaller barrier to get over, it has a larger rate constant when it is going in the forward direction. Within this, we've been exploring what happens when we have a single collision. Single collision meaning we didn't have a large concentration of the different atoms involved. The PhET sim allows us to look at many collisions as well. Before we do that, share your thoughts right now. What is your understanding on the single collision? What questions do you have? Is this making sense to you?